So now we try to solve this question, the same question using train A as the frame of reference, which in other words means that the observer's point of view is train A. Now, before we go, much into this frame of reference, see, I do understand that for some of us, this frame of reference and topics like inertial and non-inertial frame, this could be overwhelming, at once, and you might be finding it very difficult to understand what's the difference in the perspective, and for that matter, what's the difference in the arithmetic calculations while solving these questions, while solving the same question using different frames. So, to make sure that we get a very clear idea about what we are about to do using train A and train B as the frame of reference, okay, we'll first try to learn in detail what is frame of reference, what are the types of frame of reference, and based on these two types, how will the calculations vary. Okay, so let's first try to understand frame of reference. So, what is a frame of reference? A frame of reference is a point of view or a background from which you observe and measure motion. Think of it like a camera angle from which you watch and describe what's happening. Okay, so every time you use you use observation in motion, always try to understand, always try to visualize that you have placed a camera at some point and you see the motion from that camera using that camera. Okay, so where the camera is placed, that place would decide the choice of frame, being inertial or non-inertial. Okay, yes, I do understand there is a bit of lack of clarity there. I'll come to it in a while. So this might be the first question that is coming to your mind while we were solving this question using train A as a frame of reference. Why do we need a frame of reference, right? The straightforward answer is because motion is not absolute. It always depends on who is observing and from where. Now, from where basically stands for the frame. Okay, you are sitting in a moving train looking at another person sitting near you. From your point of view, which means if you place a camera in your seat and if you observe the person sitting near you, the person is not moving because the camera will see that the person is at rest, right? But to someone standing on the platform, both of you are moving with the train, which means if you see the motion from a camera which is placed on the platform, what will you see? You will see that both these persons are moving along with the train, right? I hope that makes sense so far. So, whether the person under observation is moving or not, or whether the object under observation is moving or not, it depends upon the frame of reference. So, the frame of reference is the moving train, the object appears to be at rest. If the frame of reference is the stationary platform, then both of the objects appear to be moving. So this motion is not absolute. In fact, no motion is absolute, and it depends totally about the frame of reference. All right. Now, how many frames of reference do we have? Well, basically, in physics, we choose frame of reference as two. One in which the frame is not speeding up or turning, and we call it as non-accelerating frame. And the other one where the frame is either speeding up or is slowing down or is turning, what we call as an accelerating frame. An non-accelerating frame is otherwise called as an inertial frame, And an accelerating frame is otherwise called as a non-inertial frame. Why? In inertial frame, Newton's laws of motion do apply, and in non-inertial frame, Newton's laws of motion do not hold true. Okay, more of this later into the discussion. So yes, I want you to make a note of this. I want you to write down this thing, or maybe you can start down from here. Just for one time to make sure that you understand what the primary need for this classification is, right? Now, what is inertial frame of reference? A frame is inertial if it is not accelerating, which means it is not speeding up, nor is it slowing down, neither is it turning. Okay, it means that it moves at a constant velocity, and also it can be at rest, which is as a special case. Examples: when an object moves in a straight line, if the observer is present in that object which is moving in a straight line, that frame is supposed to be an inertial frame. If an observer is present in an object which is moving at a constant speed, if the same person is present in an object which is undergoing a motion which is not turning, not jerking, that also would be a. Okay. Now, more on jerking when we discuss problems based on IIT Advanced. Now, let us not go into no turning and jerking here. Now, turning definitely would be questions when we discuss uniform circular motion. Well, not here. Okay. So yes. Now, what is a non-inertial frame of reference? Yes, of course, the opposite of this, right? So if the motion of an object, say instance a car, is such that it speeds up suddenly, or it brakes, which means slow down suddenly, or it turns a corner, or technical word says negotiating a corner, or it moves in a circle even at constant speed. Now this phrase is really important. It moves in a circle even at a constant speed, then it becomes a non-inertial frame because it is accelerating. So even at constant speed in linear motion is inertial, even at constant speed in circular motion is non-inertial. Hope that makes sense. Yes, I want you to make a note of this as well. See, these are potential assertion reasoning questions, right? Or maybe statement 1, statement 2 type of questions. Right. Now let's just compare this. Now, if you have not taken down any of the above, points, please make sure that you take these at least. A frame which is not accelerating is inertial, which is accelerating is non-inertial. A frame which is at constant velocity or is at rest is inertial. Something which is speeding up or speeding down or slowing down or is changing its direction, negotiating a curve, is non-inertial. Newton's law holds true in inertial frame. Newton's law do not hold true in non-inertial frame because a frictious force comes into picture, or a pseudo force that comes into picture. Pseudo force is not required in inertial frame. Pseudo force is definitely required in non-inertial frame. The classical example of a pseudo force will be the centrifugal force, which appears in circular motion. A person standing still on the ground is an inertial frame. A person observing the motion while he is on a rotating merry-go-round is a non-inertial frame. Now, you might be wondering, when a person is standing still on the ground is part of the earth is rotating, and therefore shouldn't that be inertial frame? Shouldn't that be non-inertial frame? So yes, that is a question. That's a question, food for your thought. Make sure that you go through the statement, think of it, come to your own interpretations. Make sure you try to reach out. If you come up with the answer, I'll be more than happy to discuss the same with you. All right? Okay. Now, how do we practically analyze the inertial and non-inertial frame? If you feel normal within a frame of observation, that becomes inertial frame. Now, what do you mean by normal? Contrast to normal, if you feel a push or a pull during the motion, which actually happens corresponding to speeding up or slowing down, that frame becomes non-inertial. All right? Okay. Now coming to this question. Is the observer in this question in a moving train which is at a constant velocity in an inertial frame? Yes, the observer inside a train at a constant velocity, which is given to us as 90 km per hour, is an inertial frame of reference. Okay. Now, how do we approach this question if it would have been phrased differently? If the train were accelerating, decelerating, or turning, it would be a non-inertial frame because frictious forces like centrifugal force would appear, and therefore Newton's laws of motion would not apply directly. Since train is moving at 90 km per hour, which is otherwise meaning that it is at constant speed and with no acceleration, train A is therefore a inertial frame of reference. So for the passenger inside this train A will not experience any frictional forces, so their frame remains inertial. Okay. Now let's continue this further. So if we have frame of reference as train A, what does it imply further? Which means if we choose frame of reference as train A, what are we trying to make, what sense are we trying to make out of it? It otherwise means that the observer's point of view is from train A. When we say we are using train A as the frame of reference, we are imagining that the passenger sitting in train A is our observer. From the passenger's point of view, train A is at rest. Any motion seen or measured is relative to this resting train A. Now, how is this resting? How is this train A at rest? That becomes really important. To understand that, let us spend some time here. Yes, see, I do understand that it's becoming really way too much for a frame of reference, but what you don't what you really don't understand is if you pay your maximum attention, if you try to make notes of this and to understand what's actually been mentioned here, this will help you a lot throughout your mechanics. It will help you in motion in a straight line, motion in a plane, and this will be the fundamental for a lot of questions that you discuss in laws of motion, friction, gravitation, right? So no matter which question you come across motion, if you understand well to use frame of reference, this would help you a lot. Okay. As usual, I'm sorry for making the explanations lengthy. I'm really sorry. Okay. So when the frame of reference is train A, how is this train A at rest? Okay. Let's try to understand that. So if we take the same example here, we have a train A and train B, which is going into opposite directions. So train A is going like this and train B is going like this, towards right and towards left. Now when we place the observer on train A, every physical quantity with regards to the motion is with respect to the observer. So the displacement is with respect to the observer. Displacement of A is with respect to the observer. Displacement of B is with respect to the observer. Velocity of A is with respect to observer. Velocity of B is with respect to observer. with respect to, which means relative velocity. Now, what is velocity of A with respect to A? Relative velocity of A with respect to A is velocity of A minus velocity of A. Are we missing anything here? Exactly. Is there any absolute velocity? No, which means this is velocity of A with respect to ground minus velocity of A with respect to ground, and therefore velocity of A with respect to ground VAG minus VAG is equal to 0. Or in other words, since A is the observer, we can say velocity of A with respect to observer is equal to 0. And if an object has a velocity equal to 0, it means that it is at rest. And since the observer is standing on train A, VAO is equal to 0, and therefore the train A is at rest. Hope that makes sense? Alright? Okay, now let's see this. What is velocity of, what is velocity of B with respect to A? Which otherwise means relative velocity of B with respect to A. We know VBA is equal to VB minus VA. Now what is VB? VB is actually VB with respect to ground, right? VB with respect to ground. And what is VA? VA is also VA with respect to ground, right? Now, what is velocity of B with respect to ground? Let's say for instance, this is moving at 10 meter per second and this is moving at 20 meter per second. A is 20, B is 10. Now, what is VBG? It is 10 minus 20, right? Is there a mistake? Exactly. Why? Because we are talking about velocity, and since velocity is a vector quantity, it should be supplied with direction. So we assume for this case that objects moving towards right is positive and towards left is negative. So VB is actually minus 10, and therefore this becomes minus 30. So it means that a train which actually is traveling at 10 meter per second, when observed from a train which is at 20 meter per second towards the opposite direction, a person inside this train would feel that the train B is approaching him at a speed of minus 30 meter per second. Repeat that, right? Make a note of that. Write it in your words. Explain that to yourself. And then maybe try changing these values and rephrase the sentence again. Do that repeatedly until the idea becomes clear to you. Or maybe catch a friend of yours and then try to explain the same thing to him or to her, and then things will become more clear to you. All right. Now let's see, what is the passenger observing? Now this is just an extension of what we discussed so far. So train A is moving at 90 km per hour and train B is moving at the opposite direction 54 km per hour. But since we are sitting inside train A, when I say we, the observer is sitting inside train A, the observer is not standing on the ground. We are observing everything from inside a moving train. The camera, right? So the camera is now placed within train A. From the passenger's point of view, train B is coming towards them. Since both trains are moving in opposite directions, train B appears faster than it actually is because both are moving away from each other relative to the ground. Now, how will it appear faster? That is where the significance of this calculation comes into picture. A train which was coming at 10 meter per second appears to be coming at minus 30 meter per second when you shift the frame of reference from the ground to the train A. Does that make sense? All right. Okay. Now, coming into the numerical part of the question. What is relative velocity of B with respect to A? VBA is equal to VB minus VA. What is VB? It is minus 54. Why Why VB? Why is VB minus? Because VB is towards left and VA is towards right. So we need to include direction. And we assume here that all motions towards left is right is positive and towards left is negative. So we get minus 54 minus plus 90, which is velocity of A, which is minus 144 kilometer per hour or minus 40 meter per second. Okay. Okay, so train B appears to move leftward at 144 km per hour or minus 40 meter per second. Now, why leftward? Again, we come into the same direction, same diagram here, because the overall motion of train B is towards the left and the direction of relative velocity is negative, which means displacement will also be negative, which means velocity is also negative, which means the motion is towards left. Why? Because we assume that towards left is negative. Okay. Right. Now, what is displacement of train B when seen from A? Displacement is a change in position. Being a vector quantity, it will have both direction and magnitude. Magnitude will say how far and direction will say which way. Which way means left or right here, right? So from the passenger's point of view, inside train A, they see train B is moving towards them. Train B appears to come from the front and pass towards the back. This is usually considered the negative direction. Let me just draw this one more time for you. So we got train A moving like this. Train B is moving like this. In result, the resultant motion is, when observed from A, will also be towards the left. Displacement here also will be towards the left, towards negative direction. And therefore, the value of displacement will have a negative in that. Okay. Now, what is relative velocity of A with respect to, okay, let us say this, we just reserve this for the future. Okay. So now the rest of the calculation here remains the same. What is that? Let me just bring the question here one time. This question directly. What is velocity of A with respect to ground? Plus 90 kilometer per hour, right? Or which is 25 meter per second, right? What is velocity of P with respect to ground? It is given to us as minus 54, right? It has to be minus. Why? Because towards left is negative, and since they are moving in opposite direction, yes, you can definitely take it the other way around as well. Shouldn't be a problem. So it is minus 54 into 5 by 18, which gives us 18 3 are 54, 15 meter per second, right? In which case, what is velocity of B with respect to A? Will be equal to velocity of B with respect to ground minus velocity of A with respect to ground, which is 15, sorry, my bad, VBG is 15 minus 15 minus plus 25, which is equal to minus 40 meter per second. Therefore, what would be displacement of B with respect to A? It will be equal to velocity of B with respect to A into time. Pretty straightforward, right? What is displacement of velocity of B with respect to A? It is minus 40. So this becomes minus 40 into, what is the time given to us here? Observation is for 8 seconds. So this is into 8, which gives us minus 320. Now you might be wondering, we don't have an answer as minus 320. Why? Because we've been asked to find out length. What is length? Length is the magnitude. So if displacement of B with respect to A is minus 320, the magnitude of this will be equal to, magnitude of minus 320, which is plus 320, which gives the correct option as option D. All right. Now we'll do the same question using the frame of reference as train B. Okay, so before you go into that, the next solution, I would personally suggest that you, if you have written down all of this, which I assume you have done, make sure that you do not wait for the next solution. Try to do the complete solution with respect to train B as a frame of reference. And if you get the same answer, well and good. And if you don't, then go to the next solution. Or maybe if you get the correct answer and yet and then you feel that you need more clarity on it, move on to the next solution. But if you are going directly, if you're planning to go directly towards the next solution, then I would suggest that is not going to help you. Okay. All right. So next up, moving to frame of reference as train B.